notes on the spectrophotometer, again, this is not something that you are going to be quizzed on. Tell me how the spectrophotometer works inside and out. That being said, on AP exams, they always have questions that deal with the techniques of things. So they might have you do a dilution math problem and then talk about, hey, they got bad results. Sources of error are always a big thing for AP. And so explain why this student got a bad result, referencing the equipment that they used. So that's why we're going to go over this a little bit. So first off, everything on this slide, except for probably the bottom part, is stuff that we went over in Chem 1. Again, we talked about wavelength of light. We talked about frequency, maybe not amplitude, kind of up and down. How big is the up, how low is the down part of a wave? But we know that light travels in waves. We have a visible spectrum, our Roy G. Biv. I show that on the slide here. Red wavelengths are longer, and therefore they are less frequent. Violet, on the other hand, are shorter and more frequent. The speed of light, 3 times 10 to the 8th meters per second. Again, it would be slower if it was traveling through matter. So light through water, light through air in this room is slightly slower. But light in a vacuum, which, for example, outer space is pretty close to a vacuum, that's how fast it would travel. Some things that we don't talk about too much in Chem 1 is that light can be absorbed by objects. Perhaps this is something that physics covers a little bit more. This color light gives off this color when it shines on things. Absorption of light is what we have to deal with, though, coming today with our spectrophotometers. Transmittance, the last term on there, so either you're absorbing light or you're letting it pass through. So are you letting it pass through? It's being transmitted. Are you absorbing it? And then dispersion, how is it being spread out if it's shining through something? The parts of the spectrophotometer, we have a very expensive light bulb in there. That light bulb needs to be warmed up for about 10 minutes before it can actually make good measurements. That's why prior to you sitting down, I asked you to turn on the spectrophotometers. That way when we are ready to go, we can just go with it. Next class, we'll probably start the day with doing stoichiometry review. Nothing in the lab has anything to do with stoichiometry. But that way we show up, we start stoich practice, and while we're practicing, we turn on the spectrophotometers, let it warm up for a little while. I can move this bottom part here a little bit. I guess you can probably see it on your screen otherwise. We can adjust what wavelengths of light are going to shine through our sample. That's what this second part, the monochromator, will do. Our sample is then what the light is going to shine through. Whatever light is able to pass through that sample is going to hit a detection field. And it's going to tell you, hey, this is how much light passed through. And then on your screen, you will be given a value, how much light actually passed through. So it seems like a fairly simple setup, but because of how sensitive that light bulb is to begin with, and that detection field has to be very good as well at what it does. It is a pretty expensive piece of equipment. That's why we can only have one per lab bench, which means today in the lab and next time we're working in groups of 4. Again, I'm not a huge fan of doing groups of 4 because sometimes we're not all doing stuff, but it's what we got to do with the equipment that we have. Now, perhaps when you were at the lab bench, you noticed we have these tiny little test tubes. They're actually called cuvettes. This is what will go inside this compartment right here. So again, there's not a lot to this machine. There's a spot there you put a small test tube in with a solution, and then there's a dial that you can adjust the frequency for. That's this part right here. Again, that's how we can adjust what wavelength we get through. I will say that that test tube fits in snug, really snug. So I might need someone with smaller fingers to take it in and take it out to prevent breaking this, which I've had happen before. Beckwith, I believe your brother was actually in a group that broke this at one point. And they broke it so bad that we could not get it out. And I had to perform surgery on one. It was actually the one that's right up there. Do you know why that one's up there? It's not working very well. I wonder why it's not working well. I took it, he didn't do it, he said, but he did come and help me perform surgery afterwards. Again, thinking about all these parts here, when you look at these two solutions right here, which one appears to be more concentrated? The one on your left or the one on your right? The one on your right. Seems like it's darker, doesn't it? It's actually the exact same molarity for both, though. It's just that you are looking through this, passing through a lot more solution. So the thinness of that test tube, that cuvette, plays a role as well. Because if I start turning it on its side, if you're looking from the top, it doesn't look actually as dark as this one here. So a lot of mathematics goes into making this machine work the way that it does. We more or less just have to make sure we know how it works. And that's this explanation right here. Again, you're not going to be testing any of that. Light passes through a sample, it hits something on the other end, it tells you how much light passed through. Boom, that's it. So if you flip to the back side, the second bullet point here hopefully makes sense to you. The more concentrated a solution is, the more light will be absorbed by it. If you're trying to shine light through a sample and not a lot is getting through the other end, that sample must be fairly dark. It must be grabbing hold of it. There's a lot of matter in between light source and detection field. If it wasn't a very concentrated solution, a lot of light would be able to pass through. So that second point is really the basis of this piece of machinery, is I can give you a solution and it can tell you how much light it absorbs. First bullet point, we're going to be doing some math within this, especially next class period, that if we have an unknown solution, which the ultimate goal of our lab is going to be, what's the concentration of blue dye in Gatorade? So we don't know the molarity of it, but we can figure it out. Because if we take a whole bunch of samples of known concentration, and this measures our absorbance, we can then do a little bit of math to figure out, hey, if I measure the absorbance of that, I can calculate what the concentration is. So that's the ultimate goal that we're doing next class period. Again, today we have to do something slightly different, which is shown in this graph right here. We have to determine what's the best wavelength of light to do our experiment in. Now that's what makes this piece of equipment a little different than other things, is that if we don't have it set up correctly, it's going to give us poor data. So day one, we are going to be creating a graph that looks something like what you see up here on the smartboard, where we want to find what is the peak absorbance value for something. Because if we know that, then we can, day two, use that wavelength for multiple concentrations of solution. So that's kind of what this slide is referring to. If we get done with day one, next class, we're going to create what's called a Beer's Law plot, which is going to be hopefully a fairly straight line, measuring concentration versus absorbance. So once we have known values down, we can take an absorbance of an unknown thing and kind of plot it into our equation for our line and solve for our concentration. Now I can go over this again before day two, but I wanted you to be aware of this. If you recall when you were doing the reading guide, it said that dilution equation, M1V1 equals M2V2, is not on your equation sheet. An equation that is on your equation sheet for AP is this one right here, so it's not one you ever have to write down. And actually, a nice thing about the equation sheets for AP is they give you the equation on the left-hand column, and on the right-hand column, they tell you what each variable means. There's a couple different ways we can use this information, so this is one equation that can solve for the absorbance of things as well. This equation I'm showing you right now, we will use on the lab second semester. First semester, I plan on using graphic analysis instead, where we don't even have to use this equation right here. Here's my last slide. We have to warm up the spectrophotometer. Some brands in them are called Spec 20s, that's why I abbreviate it that way sometimes. On the spectrophotometer, you have your open and shut compartment to put your cuvette of solution. You have a dial to adjust your wavelength, and then you have a single button on the top part. It's the 0 button. Remember, if you had to find the mass of a solid solute on a scale, you wouldn't put the solute directly on the scale, you put a weighing boat on it first. But then you don't want the weighing boat mass to be part of the total mass. So on a scale, you hit the 0 button, it gets rid of the weighing boat, and now you can just add. Spectrophotometer does the same thing. you make a solution, you have water and solute. Well, water has matter. It absorbs some light. But we don't want the water's absorbance to play any role in our data. We only want the blue dye. That's why we will zero our spectrophotometer with distilled water. Then we get rid of that. Quite frankly, not only does the light pass through the water, but what else does the light pass through when we have our sample in our little test tube? The glass, the test tube itself. We want to get rid of that part also. We want to only measure with this piece of equipment the blue dyes absorbing of light. So that's why we have a 0 button, just like a scale. Fingerprints. This is a very sophisticated piece of equipment. Again, 1 button, 1 dial, you're like, yeah, it's not that special. If you have fingerprints on your cuvette, it will change your absorbance. That's why you're usually going to have a paper towel, and every time you handle it, you're going to have to wipe it off. Now, if you'll notice, when I show you a cuvette, there's kind of a point when they have their own little marking on the cuvette, the light's not going to pass up that high. So if you can hold it towards the top, you're usually fine, but usually people just wipe it off before they set it in. I try to point this in the same direction every time just to make sure I'm consistent with how the glass itself is as well. There's little things though. If you take future chemistry courses in college, again, in a couple class periods, I'm going to show you the scales that we use in AP Chem that go up to the thousandth of a gram. I've had scales that go even further than that, where your fingerprints on a scale can affect the results. So we got to get rid of the fingerprints part. You rinse your cuvette. So in other words, what you will be doing today is you'll be putting this blue solution in one of your test tubes. But you don't know what was in here prior. Especially if it's a 3rd hour class today, you guys are going to rinse out your stuff when you're done like a good student would do. But if you rinse something out, there's a little bit of water left on the bottom. And then if you add the blue dye solution, and it's a known molarity, well, if there's a little bit of water on the bottom, what did you just do to your solution? We diluted it. I mean, the thing that we just did a reading about. And if you dilute it, now you've made it not what it's supposed to be. So you usually pour a little bit in. I have pipettes, you can squirt some in, you roll it around, you dump it out, and then you fill it back up. A lot of things that we do at times in class in the lab seem like it's wasteful. Oh, we're throwing away weighing bullets. Oh, we're throwing away pipettes. Oh, we're rinsing out a solution and we're just dumping that solution out right away. We do it so we can get good data. If we don't do it, we get poor data. And just like I've been trying to harp on Chem 1 students, poor data leads to poor results, leads to poor conclusions. What we're going to do today is the second to last bullet point. We're going to test one sample at multiple wavelengths to determine the best wavelength. Day 2, we're going to test a lot of different concentrations of solutions instead. So what I'd like you to do is have out the lab packet that you picked up on the way in.